Good morning from the Hellenic Mediterranean University and the Athena talks. We are very happy to continue. This is the last Athena talk for 2024, not the last one for 2024. Our program continues until the end of July 2025. We are very happy to have with us a Greek professor, a Greek from the diaspora. Also, it's like a priority for the current Greek government to have links and collaborations with Greeks all over the world. We have together with us Associate Professor Yannis Markonis, but I will provide the floor to my colleague, Professor Yannis Daliakopoulos, to introduce our today's speaker, since he is his suggestion and contribution. So, Yannis, the floor is yours.
Thank you, Kostas. It's also a great pleasure to host today Yannis Markonis, who is an old colleague from the Technical University of Crete. Today, he's an associate professor in the Faculty of Environmental Sciences at the Czech University of Life Sciences in Prague. His research focuses mostly on multiscale variability of the water cycle and its interaction with climate. He works with European droughts. He works with long-term changes in the Europe's hydroclimate and weather. But I know that he also works in the hydrology of other planets. So it's my pleasure to introduce Yannis. Yannis, the floor is yours.
Thank you very much, Yannis. Thanks a lot for the invitation, and let me also from my side to congratulate you for this great initiative. It's very useful to the community, and let me share my screen. So today we won't speak about other planets. We will stay to Earth, and we will speak about hydroclimatic extremes, focusing mainly to floods and droughts and their relationship to water cycle changes, terrestrial water cycle changes, and as well as these links with global warming, with the rise of the temperature. So by the end of this talk, we expect to have an understanding of how the increase in atmospheric temperature can affect changes in water cycle, and what is most important for human societies, changes to its extremes, droughts and floods. Sorry. So So the overview of today's talk is going to be today's talk will be divided into three parts. We will start with a brief description of the theoretical background regarding hydrological cycle, extreme hydroclimatic events, and how they are linked to global warming. And then we will provide some empirical evidence about how floods and drought change at global scale, following with a focus over Europe, where we have more information, or it's one of the regions that we have more information, so it makes sense to look closely to regional scale and Europe. We will conclude with a synthesis of how floods and droughts combine together, discuss some ideas for future research and the challenges we are facing. So let's start with the theoretical background. All of us have some understanding of the water cycle. I would like to give some focus into two things in this representation, like conceptual representation of the global water cycle, that has also some quantitative elements. So we can see that when we're speaking about water cycle, we're speaking about fluxes, which are the arrows, and as well as storage, which is the boxes. So, and when we are speaking about what is very relevant to this talk and the changes of extremes over land, is looking at the amount of water that can be stored in the atmosphere as vapor, which is like this 3,000 cubic kilometers over land, compared to the amount of precipitation that falls over land, which is quite bigger. So this is the fluxes, this is the land, this is the storage, sorry, over land. So of course there are many more fluxes over both over land and ocean, different processes. But when it comes to hydrology, we usually like the main conceptualization, the main modeling that we do of this complex system is quite simpler. So we create a mass balance that has few terms, which is the precipitation, evaporation, runoff, and the changes in storage. So when we are looking at the changes in the water cycle over land, actually we are looking at changes over these variables. And for example, for flood is quite evident that we are going to look to runoff, but for drought it becomes a little more tricky because we are looking also to precipitation, evaporation, and runoff. And I would like to focus more into this one because flood is quite intuitive phenomenon. When you have the runoff surpassing the banks of the river, then it's like easy to define what is flood. But when we go to drought, then the threshold is quite arbitrary. So just set a value for water to be below this threshold. But even so, it's like quite there are multiple ways to define this threshold. So we can speak about, if we're speaking about precipitation in the previous mass balance that I shared. If we're talking about precipitation, then we have what we call meteorological drought. Then if we move to runoff, let's say we have runoff below certain threshold, we have hydrological drought. And if we're speaking about soil moisture, we have agricultural drought. I'm sharing these definitions because I want to give, these are the three basic definitions, let's say, because I want to show how difficult it is to define drought. And this means that it's also difficult to define a change drought. And what makes things even more complex is that if we see, for example, a typical drought, one of the most extreme droughts that happened in Europe in 2003, we can see that depending on the variable, each drought type has different onset and different termination. So if we're speaking about precipitation, this is what happened in the beginning. And we have deficits in precipitations, which were followed by deficits in runoff, which were followed by, in deficits in soil moisture. So we had a cascading evolution of the phenomenon. And this is what makes drought quite difficult to define and study. Now, moving to this was about the water cycle, its extremes, flood and drought over land. What about global warming and temperature increase? When we are looking at changes of water of atmospheric moisture in the atmosphere. This is well defined and well explained in thermodynamics by the Clausius-Clapeyron equation. This is the formulation that contains the saturation vapor pressure, latent heat, sorry for the Greek, and temperature and change in volume during phase transition. Why this is important? Because this relationship, the saturation vapor pressure, gives us the amount of water that can be stored in the atmosphere. And this can be simplified to a simple exponential relationship that gives this kind of relationship between temperature and saturation vapor pressure. That actually says that the warmer the temperature, more water can be stored in the atmosphere. And this is why this is about this part of the terrestrial water cycle. So this number over here, 3, increases the warmer the temperature it is. Based on thermodynamics, it is estimated that for 1 degree of in the temperature, there's 7% increase in the atmosphere. But the question is that, okay, how does this increase in the atmospheric moisture relates to the other components of the water cycle? Does this mean that we are going to have heavier precipitation, which can result to heavier or to more extreme floods? Or why this should relate to extreme drought, for example? So all of this is like very clear in thermodynamics. There are also the dynamic components that affect the complex system that, of global water cycle and water availability and extremes over land. And while all of this, it's quite there are some there's a lot of evidence based on computer models, Earth system models, that show both increases in heavy precipitation and to drought events, mainly because for different reasons. Like we can understand that more water can, like we can intuitively understand that more water can result to heavier precipitation because there's more water in the atmosphere. But there is also the scientific hypothesis that since there is more the balance of water between the land and the atmosphere changes, there's higher demand, atmospheric demand for water, then this results to dry, to acidification over certain regions. But the best way, since like it's quite complex, this is not formulated due to purely equations, but it's also purely thermodynamic equations. But it's also, as I said, relates to dynamic components. The best way is to search and look for empirical evidence all over the globe. So recently there have been some studies that they were studying the global changes in floods and their drivers. The title for the slides from now on, most of them are the titles of the papers that you can have a look if you are interested too. And yeah, let me take this opportunity to say that if anyone is interested, I will be very happy to share my presentation by if someone wants to reach out by mail. So the findings in the first study that I'm going to share actually is showing a decrease in global in floods globally, and this was quite surprising because we expected them, based on the theoretical background on the model simulations, to rise. And in this study, we can see that unfortunately, there are not many locations worldwide, which is something that we will further discuss. But there was quite significant signal of slight decrease in floods, which was further supported by another study, which, although it showed an increase in precipitation, which is what we expected, we don't see a decrease, we see actually no change in the number of floods. But when the researchers looked into the characteristics of these floods at global scale, they have noticed that actually there has been a significant decrease, which is here, in the floods caused by snowmelt or precipitation or heavy snowmelt or precipitation over snow. There have been an increase in the precipitation in floods caused by precipitation, by extreme precipitation. So this implied that while we are not seeing some impressive changes in floods globally, we're experiencing a change in their properties. Again, we can see that the stations, the locations that were investigated are more or less the same, mainly Northern America and Europe. Now, moving to droughts, we more or less we are seeing a similar pattern. There was this paper, like a quite famous paper back to 2012, that was claiming that there's very small changes in global drought over the past 6 years, from 1950 to 2010. And actually, it was showing that depending on how you define drought, then you get completely different results. So this is why I explain why drought is can be quite elusive to realistically identify trends in its change. Again, more recent research from Vicente Serrano showed that if we go also to and as we see here, I forgot to say that. As we see here, we can see that we are looking at a global data with high coverage because they are using some interpolation techniques plus hydrological modeling. When we go to stations, we see even more profound drop into global drought. But again, we have the same situation. Let's say like we have most of stations in Northern America and Europe, and here we have also a lot of stations in Australia. So based on these studies, we are seeing that there are some signals of drop in the extremes, while we will expect some different. But all of the studies suffer from the same limitation. The coverage of stations, which gives us the opportunity to look more into regional changes, because we spoke about flood that we are seeing some changes in the characteristics. So if we focus more into the regions that we have more data, perhaps we can understand what is happening and why we get this signal at global scale. So let's move to Europe. And this is some work we did 5 years ago. And actually, we saw that if we use paleoclimatic reconstructions, like indirect ways to measure Europe's hydroclimatic variability, we can see that actually these values over here, the last 90 years, like each point represents 30-year time, we see that we are in a quite wet period, but there are also some droughts. And if we look more at the spatial characteristics, we can see why this is so wet. We can see extremely wet conditions, but especially for the last 30 years of this study, 1983 to 2012, we see this dipole, like we have quite dry conditions over Mediterranean mostly, and wet conditions, extreme wet conditions over Central and Northern Europe. So this was quite interesting because we knew that from 2000 and after that Europe was hit by some severe droughts, but we couldn't see this in the long-term data. Speaking about floods, this was also kind of confirmed by the study of Plaslu et al. This is from one group that's like one of the most prestigious groups like in floods over Europe, the European domain. They have done a similar study, which again, with the use of paleoclimatic data, show which periods appear to be the most extreme in terms of flood events. And we can see that last 25 years here, that like there's a period over Europe that it is like it is something similar occurred only once in the last 500 years. So there's good agreement between our results saying that, okay, this is a period, it's a wet period over Europe, and it's like active period in terms of floods when you qualitatively, because this is more qualitative study, compare the amount of floods and their intensity with the past 500 years. But does this mean that floods are increasing? Now, same group have seen, this is on the left panel, have showed that in most of the Europe, this is not happening. Like we have some significant decrease in floods, except for this part of Europe, like Central Europe and British Isles, that there's increase in floods. What is interesting though is that like in a different study, they have already seen that the characteristics of floods are changing, similar to what there has been observed in the global study I showed before, but here it was more about the timing of the droughts, so the floods. So floods were occurring sooner or later, depending on the region, due to temperature controls. So despite the fact that the amount of floods wasn't changing, or the severity of floods wasn't changing that much, the fact that the timing of floods was changing had a significant impact to water management and flood protection in general. Moving to droughts now, as I said that we knew that we were in a wet period, but at the same time there have been some extreme drought over Europe since 2000, in the last millennium, and so this made us wonder to see like why this is happening, like how this can be possible. And what we did is like we tried to reconstruct the hydroclimatology of Europe for the last 250 years and run a hydrological model and see how these floods, droughts, look like in the long-term perspective. And we were surprised to see that the 2003 and 2015 drought, unfortunately, this was like, this study ended at 2018, so it didn't have the very recent extreme droughts. But these two droughts that were considered quite extreme, we realized that it's like quite normal, let's say, droughts compared to the droughts of the last 250 years, which were quite more severe. This is the vertical axis, and quite more extended, which is the horizontal axis. But what we also found out at the same time is that this, if we just look into the droughts that occur in the vegetation period, which is the period starting in April and ends in September, then these droughts become quite extreme. These are the droughts that are marked here with the white points. So you can see that both for precipitation, runoff, soil moisture, and both for Central Europe, Mediterranean, and the whole Europe, these droughts now start to become quite more unique, which made us move to the next step and focus more into this type of droughts, where we have used some machine learning algorithms to classify the droughts based on their starting and ending month. Here you can see the clusters of the droughts, and based on their duration. And we compared these three periods to see how different types of droughts, based on how the machine learning algorithm classified them. This was an unsupervised classification, meaning that we didn't provide any, let's say, guideline how the clusters should be formed, how these clusters changed. And first of all, we have seen three main classes or clusters of drought. These warm season droughts that start in April and end in August or September. And the other two types were the more traditional, let's say, type of droughts that are longer and start either in autumn or in winter. So what was interesting is that the warm season droughts appear to be replacing the traditional droughts, which are longer, but could be less severe. And we have realized that this type of drought, the warm season droughts, are also affecting different types of droughts. So it's always droughts about lack of precipitation. There is no rainfall, so it's like this is the usual reason that a drought starts. But for these warm season droughts, we have seen that they are also combined with very high temperatures, very high evaporation, which has been, as we see here, increasing in the last years. And this could be a link to either increase in temperature or global warming, or changes in atmospheric circulation, which means that due to changes in atmospheric circulation, we have more sunny days, which creates more evaporation and enhances the effect of drought, or it could be both. It's hard to say, and we didn't look that deep into the atmospheric drivers of the drought, but it was clear, very clear, and this is the last panel here, that we have been experiencing a significant increase in agricultural drought, meaning the type of drought that depletes soil moisture. So this has also severe sequences in agriculture, because also it happens through the vegetation period. So what we've been seeing is that in both floods and droughts, it's quite difficult to say that there is a very clear trend of increase or decrease. But at the same time, we see changes in their properties and in their dynamics. And the question is, okay, how this can be aligned with changes in atmospheric moisture that we spoke before, due to the increase in the temperature. How it is possible, so if there is more water, to have at the same time changes in floods and droughts? And actually there has been a very recent idea about that. And this is the looking into the combination of flood and drought, and actually drought and flood at the same time, or drought that is followed by some flood. And although this is very initial, there are very initial preliminary results into this field, there are certain regions that we can see this happening, again suffering from the data set limitations, which actually is based on an older idea from Trenberth, which says that, okay, if we see increases in precipitation and more heavy events, then we can have, let's say, this is a hypothetical scenario, of course, that all the precipitation falls into 2 days. So in the rest of the, let's say, month, you can have drought, which is then followed by some extreme flooding. So if the nature of precipitation changes and is not uniformly distributed all over the month, then we could experience this kind of combination of drought and flood events. So this could be an explanation of all of these changes, and this seems quite plausible based on the current theory and empirical findings. But it would also mean a decrease in the number of wet days. So we have less wet days because that's only 2 compared to the, I don't know, 15 that are here, which is something that we actually we are not finding empirically, because in an older work that we have done, we have seen and we have studied, let's say, the global changes in precipitation as well. Like here's the time series of precipitation. Here are its distribution per year. If we see the amount of precipitation at each year, so the extreme values will be here, and we have just see how its distribution, its quantile changes. So the heaviest quantiles, the more extreme precipitation, we can see that increases more compared to the lowest ones, and this is another way to say it. But the problem, the challenge, let's say here, is that we have seen an increase in total precipitation, but we have seen also an increase in the wet days. We haven't seen the decrease in the wet days that we expected to see. So this is something that could be part of future research. Look more into it, because here we just used one data set. Perhaps it was like problem of data set. And as far as I know, there are not many studies that are examining how wet days are changing globally. This is one part that could shed more light into this drought and flood to drought situation. Another path of research that is interesting to us is what happens when we are looking at the extreme evaporation. So we had this idea of clustering in evaporation, the same that we study, let's say, extreme precipitation, and whether these extreme evaporation events could lead to extreme precipitation due to land atmospheric feedbacks. This is another path that we think that it might give some promising results. But the main challenge that both directions face, at least from our side, is the data situation. So we already spoke that there are very few stations, or sorry, no, there are many stations, but there are specific locations that we have many stations and good understanding of how precipitation and evaporation change. But when we look at, here's a study for precipitation. When we look at the global scale, we see big disagreement. And in this study, we have used 17 precipitation data sets, almost all the state-of-the-art data sets, trying to measure their agreement or disagreement across the globe. And what was a big surprise for us is that we knew that North America, as we discussed, has a lot of stations, so there's high data set agreement. But this is not the case for Europe, that we still have many stations, but we can see that the data set agreement is quite lower. Other results were quite more expected, like the mountain regions are showing very low data set agreement, or the high latitude due to the snow effect. So definitely more can be done when it comes to dataset uncertainty. It's something that is also quite realistic to achieve in the next years. But it has been quite a bit surprise for us that precipitation, which is the most studied variable in water cycle, the studies appears to still have so big differences. And when we move to other variables like evaporation, things appear even worse. Here's a study of how evaporation changes all over the globe. And we see that there is a big discrepancy when we see the trend direction, the trend value. Speaking with some top experts in the field, like these values, like anything above 2 doesn't make any sense at all. But also it's like quite intriguing to see that even if we see the sign of the evaporation data sets, like almost half of the globe, they don't agree in the direction of change. So it needs a lot of caution when we are using these global data sets, because despite the progress, and there has been huge progress so far, they still appear to give very, very different results. So to wrap up, based on let's say the state of the art and personal experience in global research on water cycle changes and how global warming affects hydroclimatic extremes, we can say that definitely there is a strong relations, theoretical justification that as the temperature increases, the hydrological cycle is changing. However, this connection becomes quite more complex when we go to the scale of the hydroclimatic extremes, and there's a lot is need to be done. It's something that is still under investigation. Now, when we are looking at the discrepancies between the data that I showed, what comes to my mind is that this is something tangible, it's something that it's realistic and should be expected to be solved in the next years, especially with the rise of the remote sensing data. But still, it is important to maintain and build stronger networks, because without networks, measuring networks, it will be impossible to improve our data. We have seen the big gaps, the global gaps that we are facing, and especially in regions like the tropics, that most of the water moves between the atmosphere and the land. And speaking about the movement of water between the atmosphere and the land, this is what we see that it is happening on the places that there is agreement between, or there's strong agreement between the data. So we can say that we can see the acceleration where we have good agreement, but still we need better coverage to make some better global conclusions, let's say, about how terrestrial water cycle is changing. And with this, I would like to thank all the people that have worked in we have collaborated in some of the results and studies that I have shared with you today. And I really hope that this talk gave you some better understanding about the changes that we are expecting, the evidence that we are observing, and the challenges that lay ahead for us. Thank you very much.
Thank you, Yannis, very much for the presentation. Now I think it's the time for questioning. So if you can stop sharing the screen, I have some questions.
Of course.
But I'm not an expert. It's going to probably some of them they are going to be very naive. But
No, I mean,
the topic is very hot, I will say. Not because of the temperatures, but also because of the theme. So if we have any questions, please write them in the chat, or you can raise your hand and ask the question directly. So I will start with my naive questions, first of all. So my first question is the following, Yannis. It's like you mentioned, and it was the first time that I can see such definitions. Water stored in the atmosphere. So how much different is this from the humidity? What is humidity and what is what are you talking about? This is my first question. Sorry about. I would like to be more clear in my mind. Then I linked by following you that sometimes less floods means that they are coming from the snow melting. This means less drinkable water, because I know that the more the snow, the more the water we have. So I would like it just to reconfirm. And my third question, I have 5 questions. Do you want me?
Okay.
No, ask from the first, and then I will take it.
Yeah, that will be better.
Yeah.
So actually, thank you for the first question, because now made me realize that it will be easier to say that we're speaking about humidity, and also gave me this idea to also explain what is the Clausius-Clapeyron thing. So when we're speaking about humidity, we're speaking, let's say, 70% humidity, right? Like, let's say quite humid day would be 85% humidity. So this relationship between temperature says what is the amount of water in the atmosphere to have 100% humidity. So as the temperature rises, this 100% humidity corresponds to more molecules of water in the atmosphere, or more mass of water in the atmosphere.
Correct.
Okay, so in warmer conditions, then you have higher maximum of humidity. So it's like and a very common example for this is like if we think when we are having a shower in our bath. Okay, so the shower in a cold, let's say in a cold day, in a winter day. So what's very common, like if you have a very hot shower, then the humidity will raise to 100%. Okay, because like the temperature increases, you have the shower, a lot of water goes in the atmosphere, in your bathroom, and then you start to see the vapors. This is like, actually you're not seeing the vapors, you're seeing the liquid water, because like 100% vapors is like fully saturated. So you start to see the water in liquid form in the atmosphere. And then when you finish with your shower, let's say, and you open a door, something like the temperature drops, right? And then you have the condensation. And this is happening because the temperature is dropping, so the maximum, the 100 saturation corresponds to different mass of water in vapor form. So condensation happens. Okay, I don't know if it was like this example was clear, but this is like when I speak for atmospheric moisture, I speak to humidity. One way to measure it is atmospheric humidity.
So is it something that we want to store more water in the atmosphere? Yes or no?
Want. In what matter even what we want?
I mean, if we can leverage it, if we can use it for any application.
Actually, this is happening in some very arid regions. I think in Peru or Chile, that they are using some methods to harvest atmospheric moisture from the atmosphere. But I cannot say, it's not my field. I cannot say if this is something that can be, large scale applicable or whatever.
Okay, Yanis, I will have more, but I will give the floor to Yanis Daliakopoulos because I can see he has some question, and then I will continue. Yanis,
Sure.
I know, Kostas, you can go on with your own, and I will
all right. Thank
follow
you.
up later. Don't worry.
So
next-
just, with yes or no, Yanis,
Okay, sure.
so less floods from snow melting means less drinkable water for us?
Let's I actually cannot say with yes or no, but I will briefly say about drinkable water that you're right. Like this is happening because you have less snow. Actually, this means less floods, less snow, less floods, and this is
Okay.
problem for drinkable water that you
Excellent.
have less snow.
Excellent. So I was wondering also if you're using any AI models in order to make prediction what is going to happen in 5 years, or what is the prediction period that the models, can provide to us.
No, we are just using for classification. So we're not using AI for forecasting. We're just using for we're looking at observational and past.
So you
data.
have, just the current situation. This is what you.
Exactly.
Do they exist? Because this is going to be very important to know how, because this will accelerate our policies on how to use water, on how many green technologies we should integrate. Do we have such a models that they can predict in the future, about the amount of floods or?
There are process-based models that they are like process-based, yeah, like Earth system models that they are looking to the future, trying to reproduce the physics, and they have very, very good results in some domains, worse in some others. But we are like, I will briefly say that when it comes to droughts, because like of the complexity, it's we get both type of results, both increase and decrease. I won't give a definite answer for droughts. For floods, they show an increase.
And regarding the current data, how do you acquire the current data? Are they satellite data? Do you have sensors in the soil that you measure the humidity or how much water do we have? How do you get the data?
There are three types mainly of data. One is like the measurement like stations on the land. There's the remote sensing data, the satellite data, and there's also the model data. So you use some of the data that you have from satellite and land, and you run a model assimilating this data. We call this reanalysis data.
And the last question that I have, I suspect you mentioned very much, or I realized this part of the presentation, how important is like to have water within the soil for the plants.
Yes, of course.
So what about the impact of the forest fires? Now we can observe very wild forest fires.
This is true.
Do they affect how much water we can store within the soil?
Again, not my field, but based on the literature that I have read, this is like there's huge impact of the wildfires in the storage, exactly due to the storage, the water stored both in the plants, but also in the root system, the root zone, and how this changes the soil properties.
Thank you. Thank you very much, Yanis. From my side,
Thank you very much.
Fully satisfied. Regarding your answers,
Thank you for the questions.
Yanis, the floor is yours now.
Thank you, Kostas. Thank you, Yanis, very much for this nice change between scales from global to local floods and droughts. I will focus in just one question. You mentioned you highlighted the lack of data sets in many regions, such as Africa, for example. I noticed wherever there are deserts and so on, which is very normal, of course. And you also mentioned the disagreement between data sets, but you said that in the next few years this is very tangible to solve this. So I was wondering, okay, what are since this is your, you can see better in the future than we can. What do you see as solutions to close these holes, to close the gaps, and also produce data sets with higher agreement?
Okay, perhaps I'm too optimistic here. I wouldn't say I look better in the future, but for me, what I was trying to say is that this is something that it is purely based on policy decision, like policy making, like improving the station. Like we know that the satellites work at some extent, so against policy about having more missions, not from us, but yeah, from the big agencies that are sending or not creating the satellites. But actually, speaking about satellites, right now we have seen a dramatic decline in the cost of satellites and their launch due to the also private sector initiatives, etc. But also these smaller satellites, the CubeSat, like you can have it quite cheaper. So like this is what makes me optimistic about the satellite era. But still, you need stations because we can see that there are big differences between the regions that they have stations and the satellites are the satellite data are calibrated and evaluated based on the stations, of course. So until we have progressed a lot in the algorithms of the satellites, we need stations. And again, I'm saying that I'm optimistic because the national collaboration, international networks have increased in the last 20 or 30 years, although the amount of stations has decreased. This is a fact. But we are seeing now more and more regions in the locations that there weren't stations before having their stations. So, and this is why I'm saying that this is something tangible, because it's something that it doesn't depend from the scientific progress per se. Like it's not that, okay, we're investigating something, if we find a better algorithm or whatever. It's a very simple thing to improve the number of stations and the international collaboration. This is why I'm saying.
Thank you very much.
Yeah.
I think probably Ms. Pistaraki would like to ask something because I think
Yes.
that you see
Nice to meet you, Yannis. Very nice presentation. Kostas, thanks for organizing. I'm an associate professor in Hellenic Mediterranean University, but I have a secondment at the ministry, and one of my expertise is disaster management, so I was very interested. I don't have an actual question, but maybe I visited recently Iceland.
Okay.
And I did glacier hiking. And actually, it's very sad, very sad, because I believe all of us should do glacier hiking to see how the glaciers are melting. Out of curiosity, because you are in this field, do you know these northern countries where we have glaciers and many amount of water, do they have any strategies or policies on how to delay the melting in case
Yeah, thank you for your question. I'm not that much into the policy making and this, but what you said is very true, and this is what also relates to Costa's question about the floods during the snow melt, and the glaciers are declining very fast, very rapidly, and we are seeing this in the high latitudes, and also, I mean, I don't believe that there are. Again, not my field, just speculating here, but I cannot see any ways, like intuitive ways to delay the melting of the glaciers. Like this is due to increasing temperature, increasing sunshine, less clouds that we are seeing also in the high latitudes. And this means that water availability becomes more scarce. Iceland doesn't have a problem with water availability, but if you go to, somewhere in lower latitudes, in regions that there were snow-based water, like snow-based regions that are start to become more rain-based, let's say, then you can see that there's going to be an issue. And then you cannot do something to stop or delay the melting, but you can start changing your water management policy to have more reservoirs and store more water, because what you have for granted is not anymore.
Thank you very much.
Thank you very much, too.
So I suspect Yannis Daliakopoulos and Yannis, we need to stop here. I mean, thank you very much, Professor Marconis, Yannis.
Thank you very much.
A nice contribution. I would like to thank again Professor Daliakopoulos also for his suggestion for you to contribute in our colloquia talks. We have agreed with Yannis Marconis because I'm recording the session. That's why I would like your commitment now.
Commitment on
We are going to continue, let's say in 2025, 2026, also in collaboration with Asteroscopio. I don't know how to say this in English.
National Observatory of
National Observatory, yes, correct. To continue these colloquia talks. I mean, this will be wonderful if we can, interinstitutional, if we can collaborate in order to continue this effort. And we're going to continue the Athena colloquia talks on the 17th of January. Hopefully, I will log in from another continent, and we're going to have Professor Raquel Mamblok from Weizmann Institute of Science in Israel, and she's going to speak to us how educators can become agents of change. And this could be the policymakers, as Yanis, you mentioned, for more innovative policies to be introduced for the sake of the climate and more things to come. So I would like to wish you Happy Christmas, Happy New Year.
Happy New Year.
Again, of course, but through this platform, I wish you all the best and take care. Bye. Thank you.
Bye-bye. Thank you. Bye-bye.